Hello everyone, I am Dr. Navneet Kaur from Department of Computer Science and Engineering, SIRT College, Bhopal. Today I'll be taking lecture on subject Digital Systems. The topic which I'll discuss in this lecture is JK flip-flop. In my previous lecture, I have already discussed what is flip-flop. Flip-flop is used to store a single bit of information. It is a sequential logic circuit which stores binary information in bitwise manner. Now, coming to JK flip-flop, it consists of two inputs and two outputs. Inputs are represented by J and K, where J represents set input and K represent reset input. And their corresponding outputs are represented by Q and Q bar, where Q and Q bar are complement of each other. Now, this is the logical circuit diagram of the JK flip-flop. In this diagram, we can see that the JK flip-flop, it consists of 4 NAND gates, and since it is a clocked circuit, clock input is given to first two NAND gates. Now, these two inputs are represented by J and K. Now, here we can see that the feedback is given from the output Q to the first NAND gate, and again the feedback is given from Q bar to the NAND gate where input J is given. We have already seen SR flip-flop. In SR flip-flop, the feedback connection is not there. It is given in the JK flip-flop because in SR flip-flop, when both the inputs S and R are 1 and 1, there is a condition which is indeterminate condition where Q and Q bar are both equal to 1. Now, to avoid that condition, the JK flip-flop is used, which is used to avoid the indeterminate condition where both inputs are 1. Now, coming to the working of the JK flip-flop, when both J and K are 0 and 0, in that case, the next output Qn plus 1 will be same as the present output Qn, when it is known as no change condition. When J is equal to 0 and K is equal to 1, in that case, the next output Qn plus 1 is 0, no matter what the current state is, which is Qn. It can be the 1 or 0. But when J is equal to 0 and K is equal to 1, the next output Qn plus 1 is always 0. And it is known as reset state. Now, when J is equal to 1 and K is equal to 0, then the next state always is equal to 1, no matter what is happening in the current state Qn. So it is known as set state. Now, in fourth condition, when J is equal to and K is equal to 1, in this case, the next state is always complement of the present state. It is known as toggle state. In this case, when present state Qn is equal to 1, the next state Qn plus 1 will be 0. Whereas if the present state is Qn is equal to 0, then the next state Qn plus 1 will always be 1. So it is known as toggle state. Now coming to the truth table, we have taken inputs J, K and Qn is the present state of the flip-flop. And this is the next state of the flip-flop, which is denoted by Qn plus 1. Now, since there are 3 variables, 8 combinations will be taken from 0, 0, 0 to 1, 1, 1. Now, here we can see when J and K both are 0, then we have seen that this is no change condition. So, in this case, the next state will be always equal to the present state. Now, since in first case we have seen that since Qn is equal to 0, Qn plus 1 will always be 0. Similarly, in second case, J and K are both equal to 0. Again, there is no change condition. So Qn is 1. Therefore, Qn plus 1 is always be 1. Now, in third and fourth condition, J is 0, K is 1. Now, whatever is the value of Qn, Qn plus 1 will always be 0. This is known as reset state. Now in fifth and sixth condition, when j is 1 and k is equal to 0, whatever is the value of Qn, Qn plus 1 will always be 1. This is known as set condition. Now in seventh and eighth case, when j and k are both equal to 1, in that case, Qn plus 1 will always be the complement of the Qn. Now here we have seen that Qn is 0, then Qn plus 1 is equal to 1. When Qn is 1, Qn plus 1 is 0. This is known as toggle state. Now if you remember SR flip-flop, in SR flip-flop, in these conditions, when j and k are both equal to 1, in that case, we come across the indeterminate condition, which is also known as forbidden state. Now, to avoid that state, JK flip-flop is used. Now, coming to the characteristic equation, now here we can see that the K map of the JK flip-flop. Now, using the combination, we can see that the characteristic equation is given by K bar Qn plus J Qn bar. Now, this is excitation table of the JK flip-flop. Here we can see that when Qn is equal to 0 and Qn plus 1 is equal to 0, then first and third condition meet the criteria. When Qn is 0 and Qn plus 1 is equal to 0, in that case, we can see that j is 0 in both the case, whereas k is 0 in first case and k is 1 in that second case. Now, here we can conclude that for Qn is equal to 0 and Qn plus 1 is equal to 0, j is always 0, whereas k can be 0 or 1. So here we can see that j is always 0 and k will be the don't care condition. Similarly, for Qn is equal to 0 and Qn plus 1 is equal to 1, j will be always 1, whereas k can be 0 or 1, so it is don't care condition. Now, when Qn is 1 and Qn plus 1 is 0, k will always be 1, whereas j can be don't care. We can check this condition. Now, for Qn is equal to 1 and Qn plus 1 is equal to 0, we can see that this condition is meeting the criteria when Qn is 1 and Qn plus 1 is 0. Again, Qn plus 1 Qn is 1 and Qn plus 1 is 0. So here we can see that k is 1 in both the condition, whereas j is 0 in first condition and it is 1 in second condition. So j can be anything where k is always equal to 1. So here we can see j is don't care, whereas k is 1. Similarly, for Qn is equal to 1 and Qn plus 1 is equal to 1, j will be don't care and k will always be 0. So this is the excitation table, which is also used for designing of the counters. Now coming to applications of JK flip-flop, counters, JK flip-flop are used in the designing of counters. Counters are used for counting of the sequences. So we can design binary synchronous and asynchronous counters using JK flip-flop. Now JK flip-flop are also used in shift registers. Registers are used to store the binary information. It is made up of flip-flop, where flip-flop is used to store a single bit of information. So registers can be designed by using JK flip-flop. Now memory units also employ JK flip-flop because memory unit consists of flip-flops to store binary information. Now by making a sequential chain of JK flip-flop, we can use it even as random access memory. Now this is all for today's lecture.